Imagine a world, a realm so different from our everyday experience, where the very fabric of reality seems to bend and break. Imagine a world where a single object can be in multiple places at once, existing in a state of shimmering possibility. And consider this, a world where simply looking at something, the act of observing, fundamentally changes what it is doing. It's as if the universe is shy, altering its behavior the moment we try to peek behind the curtain. This is not science fiction, this is the universe at its most fundamental level. The quantum world, a realm of subatomic particles and bizarre phenomena. It's happening all around you right now, an invisible dance of energy and matter that underpins everything we see and touch. To truly understand the cosmos, to grasp the nature of reality itself, we must journey down to the very building blocks of matter, to the infinitesimally small world that governs the large. Quantum physics, with its elegant equations and mind-bending concepts, describes the behavior of the universe's smallest components. Atoms, the fundamental units of matter, electrons, those tiny particles zipping around the nucleus, defining the chemical properties of everything, and photons, the packets of light that carry energy across the vastness of space. These are the key players, the characters in the quantum drama, and they don't play by the rules we're used to in our everyday lives. They operate under a different set of laws, a different logic. At this scale, reality is no longer a fixed, predictable thing. Instead, it is governed by probability and uncertainty, by the inherent fuzziness of the quantum realm. The concrete certainties of our big world, the solid objects and predictable trajectories, dissolve into a haze of possibilities, a spectrum of potential outcomes. Prepare to have your mind stretched, to question everything you thought you knew about the nature of reality. Prepare to be amazed as we explore a reality that challenges our perception of what is real, a reality that exists beyond our everyday senses. The laws of quantum mechanics are not just a strange footnote, an oddity relegated to textbooks. They are the fundamental grammar of the universe, the underlying rules that govern everything from the smallest particle to the largest galaxy. They dictate how stars shine, how they generate the energy that lights up the cosmos, how molecules bond, forming the complex structures that make up all matter, and how the universe evolved from the Big Bang, from a singularity to the vast expanse we observe today. The grandest cosmic phenomena, the swirling galaxies and the explosive supernovas, are all built upon this bizarre quantum foundation. Our journey begins by letting go of our common-sense assumptions, by embracing the strangeness and wonder of the quantum world. Welcome to the quantum world, a place where the impossible becomes possible. Let's dive in and explore the mysteries that await us at the smallest scales. For centuries, Newton's classical physics gave us a clockwork universe, a vision of reality governed by precise, predictable laws. It was an elegant and seemingly complete system, predictable, definite, and reliable. Every cause had a definite effect, and the future, in principle, could be known with absolute certainty. It worked perfectly for big things, from baseballs soaring through the air to the majestic dance of galaxies across the cosmos. Classical physics was the undisputed king of the macroscopic world, but when scientists, driven by insatiable curiosity, began to probe the atom, a realm far beyond our everyday senses, they found electrons didn't behave like tiny planets obediently orbiting a miniature sun. Instead, they exhibited bizarre and perplexing behaviors. Classical physics, with its neat and tidy rules, simply couldn't explain their strange behavior. The old framework began to crumble. Nature, it seemed, uses one set of laws for the big stuff, the world we can see and touch, and a much weirder, more counterintuitive set for the small, quantum mechanics. This new physics embraced uncertainty and probability. In the classical world, things are definite. Objects have specific locations and properties. For example, a car is either in the garage or it's not. There's no ambiguity. But in the quantum world, particles like electrons don't have a single defined location. Instead, they exist as a wave of possibilities, a superposition of states. They don't have a definite position until we measure them, until we force them to choose a single location. Quantum physics reveals a universe of probabilities and inherent fuzziness, where certainty is replaced by likelihood. It's like a weather forecast, not a map, dealing in likelihoods, not certainties. We can predict the chance of rain, but not guarantee it. This probabilistic nature is not just a quirk, it's at the very heart of the quantum world, woven into the fabric of reality at the smallest scales. It's a fundamental shift in our understanding of existence, forcing us to rethink our most basic assumptions about how the universe works. The rules of the very small, the quantum realm, are profoundly different, almost alien, compared to our everyday experience of the classical world. One of the first quantum puzzles, a concept that truly challenged classical physics, was wave-particle duality. This revolutionary idea suggested that light and matter could exhibit properties of both waves and particles, blurring the lines of what we thought we knew. Electrons and photons, the fundamental building blocks of light, can act like particles or waves, displaying interference and diffraction patterns just like water waves, depending on how we observe them. The act of observation itself seems to influence their behavior, a concept that baffled scientists for decades. Before you measure a quantum particle, before it interacts with any measuring device, it can exist in all its possible states at once, a blurry mixture of every potential outcome. This mind-bending concept is called superposition. It's a cornerstone of quantum mechanics. Think of it like a spinning coin. It's simultaneously both heads and tails. An equal probability of either outcome existing at the same time, until it lands. Only when we observe it, when we force it to interact with the macroscopic world, does it settle or collapse into one definite state. Then there's entanglement, perhaps the strangest phenomenon of all. It describes how two particles can become inextricably linked, sharing the same quantum existence, regardless of the distance separating them. This connection persists even across vast distances, spanning light-years of space. If you measure one, you instantly know the state of the other, as if they were communicating faster than light. No matter how far apart they are, it's an instantaneous correlation. Even Einstein, one of the greatest minds in physics, called this spooky action at a distance. He struggled to reconcile it with his theory of relativity, but entanglement is real, confirmed by countless experiments, and is now being harnessed to develop revolutionary quantum computers. These machines leverage the power of superposition and entanglement to solve complex problems that are currently impossible for even the most powerful supercomputers. The inherent weirdness of the quantum world, once a source of confusion and debate, is now a powerful tool for building the future of technology and computation. What once seemed like the realm of science fiction, a far-off dream of impossible technologies, is rapidly becoming a tangible reality. Quantum strangeness is no longer just a theoretical curiosity, it's being actively put to work, promising to revolutionize fields from medicine to materials science. In the quantum realm, observation isn't passive, it changes what you see. To detect an electron, you must interact with it, which alters its state. This leads to Heisenberg's uncertainty principle. You can't precisely know both a particle's position and momentum at the same time. It's not a flaw in our instruments, it's a fundamental property of nature. Any interaction, not just a conscious observer, can force a particle out of superposition. This process, called decoherence, is why we don't see quantum weirdness in daily life. Large objects interact constantly with their environment, collapsing quantum possibilities into classical reality. Quantum mechanics is built on rigorous mathematics and experiment. It's one of the most successful theories in science, making astonishingly accurate predictions. The strangeness isn't a weakness, it's a window into the true nature of reality. At its deepest level, the universe defies common sense. The observer effect is a fundamental part of the quantum story. Quantum mechanics isn't just a curiosity, it powers our modern world. Your smartphone, computer, and the internet all rely on quantum physics. Transistors and microchips work because we control electrons using quantum rules. Medical imaging, lasers, and even GPS depend on quantum principles. The quantum world is the engine of our technological civilization. Quantum physics also forces us to confront deep questions. Is reality fundamentally random? Does the universe exist if no one is looking? It blurs the line between observer and observed, challenging our ideas of cause and effect. Quantum mechanics is the most successful scientific theory ever created. It keeps pushing the boundaries of knowledge, opening new frontiers in computing, medicine, and our understanding of the cosmos. The journey into the quantum realm is a journey into the heart of reality, and that journey is far from over.